Following on from the previous tutorial, we're going to produce a shear force and bending moment diagram for the beams shown on the screen. This time we not only have point loads, but we also have a uniform distributed load. So we have an 850 Newton force 2 meters from the left hand support, a 420 Newton force 4 meters from the left hand support, and the beam itself is 5 meters long. Now, one of the things that we've talked about previously is that in order to calculate the support reactions at the left and right hand support, we first need to replace the UDL with an equivalent point load. So if we add to our sketch the things that we're trying to find to begin with, we're trying to find the reaction force at the left hand support, which I'll call RA, and we're trying to find the reaction force at the right hand support, which I'm going to call RB. So before we can calculate the reaction forces at the left and right hand side of that beam, we're going to replace our UDL with an equivalent point load. Now if we look at our diagram there, we can see that the length of our beam is 5 meters because we have a 2 meter section plus a 2 meter section plus a 1 meter section. So the total length of our beam is 5 meters. And we want to find the size of the equivalent point load that will replace our 150 Newton per meter UDL. Well, the weight of the equivalent point load is going to be the weight per meter times the length of the beam, or the length of the UDL. In this instance, the length of the UDL is the length of the beam because it's distributed across the full length. So what we have is the equivalent point load is going to be 150 times 5, which is 750 newtons. Now I need to add that to the beam, but I need to add it at the centre of the UDL. Now with the UDL and the beam being 5 meters long, I'm going to need to add that 2.5 meters from either the left or right hand support. So it's going to be around there. The magnitude is 750 newtons and the distance from the left hand support is 2.5 meters. Now it's important to point out that I'm going to replace that UDL with an equivalent point load in order to calculate RA and RB, but I'll then have to re-evaluate the UDL when I come to produce my shear force and bending moment diagrams. So I'm going to leave that 750 Newton force on temporarily, and then once we've calculated the support reactions, I'm going to need to remove that in order to produce my shear force and bending moment diagrams. But let's move on and calculate our support reactions at the left and right hand support. And as usual, the first thing I'm going to do is I'm going to take moments about the left hand support, or about A. So we can say that the sum of the moments in the clockwise direction equals the sum of the moments in the anti-clockwise direction, specifying that I'm doing that about point A. And the sum of the moments in the clockwise direction, well, I have 3 forces causing clockwise moments. I have an 850 Newton force at a distance of 2 meters. I have a 420 Newton force at a distance of 4 meters. And I also have my UDL, which is a 750 Newton equivalent point load at a distance of 2.5 meters. And all of that is being balanced by the anti-clockwise moment caused by RB. That's the only force causing an anti-clockwise moment. And its distance from the pivot, or its distance from the left-hand support, is 5 meters. Well, 5RB is the same as writing RB times 5. Let's simplify the left-hand side to give 5255. So I'm going to get 5255 equals 5RB. And because I have a simple linear equation there, all I need to do to each side to get RB on its own is divide by 5. So RB is 5255 over 5, which is 1051 newtons. Next, I'm going to use the second condition, which tells me that the sum of the forces pushing downwards equals the sum of the forces pushing upwards. Now, pushing downwards, I have 850 newtons, 420 newtons, and 750 newtons. The important thing to remember for this stage is that we're evaluating the forces, not the turning moments. I have 2 forces pushing upwards. I have RA, which I don't yet know, and I have RB, which I've just calculated to be 1051. Simplifying the left-hand side, I get 2020. So I'm going to have 2020 equals RA plus 1051. Therefore, to get RA on its own this time, I need to subtract 1051 from each side. So 2020 minus 1051 equals 969 newtons. Now I'm going to add those two forces to the diagram. So RA is 969 newtons. Make sure you get these around the right way. And RB is 1051 newtons. Now, having done that, I'm going to clear some space on the right hand side, but I'm also going to remove that equivalent point load because we're going to be evaluating the UDL differently in this next section. Now, it's important to mention that all of the rules we discussed in the previous tutorial are going to apply to this tutorial. So we're going to imagine ourselves stood on the left hand support, and we're going to imagine ourselves moving from left to right, and as we do so, we're going to be looking left. Now, in doing so, we can only see the forces that are in front of us. So when we move off of the left hand support, we can only see RA. When we move a metre along, we're only going to be able to see RA and a portion of the UDL. So the process that we're going to follow is exactly the same as in the previous video. We have the same conventions to adhere to. So for shear forces, we have this convention here, where forces that push the left side up relative to the right, or the right side down relative to the left, cause positive shear, and vice versa for negative shear. And for bending, we have our convention where any force that causes the beam to sag is causing positive bending, and any force that causes the beam to hog is causing negative bending. So we're going to apply the same conventions again this time. I've also set up an area directly below my diagram for my shear force and bending moment diagrams, and as you can see, all I've done there is I've projected a line down from each of the point loads. So I've projected a line down from the right hand support, I've projected a line down from the left hand support, I've projected a line down from the 420 Newton force, and all that's left for me to do is project a line down from the 850 Newton force. So we only project those lines down at each of the point loads. So now let's imagine ourselves moving from left to right. So the first thing that we do is we step off of that left hand support. As soon as we step off of that left hand support, we can see RA. Now RA is pushing the left side up relative to the right, or relative to the position where we're stood, and it has a magnitude of 969 newtons. So on our shear force diagram, we're going to go up into the positive region, and we're going to go up by 969 newtons. Now when we continue moving from left to right, the further we travel along that 2 metre section, the more of the UDL we can see. We've already said that the UDL is 150 newtons for every metre. So if we imagine we've just stepped off of the left hand support, we can't see any of the UDL. If we travel half a metre, then we can see 75 newtons of it. If we travel 1 metre, we can see 150 newtons, and so on the further along we go. It isn't until we get to the 850 Newton force that we can see that full 2 metre section of UDL. Now that full 2 metre section of UDL is going to have a weight of 300 newtons. So the way we represent that on our shear force diagram is at the left hand side of that UDL we can see none of the UDL. At the right hand side of that UDL we can see all 2 metres or 300 newtons worth. So we need to come down at an angle like so. And if we sketch that as a triangle, here we have minus 300. And if we've come down 300 from 969, we're going to be at 669. Now that brings us to the next point load, because as we continue moving from left to right, we're going to be able to see the 850 Newton force, which is pushing the left side down relative to the right. So the way that we would represent this on our shear force diagram is a line downwards 850 newtons. So we're coming down again. This time we're coming down minus 850 for that point load. So in my calculator, I have 669, which was the 969 minus 300. And from that, I need to minus another 850 for that point load. And it's going to take me into the negative region. And in fact, it takes me to minus 181. Now here's the important thing. We've already evaluated this 2 meters worth of UDL. But as we move between the 850 Newton force and the 420 Newton force, we're going to traverse another 2 meters. And in doing so, we're going to pass another 2 meters worth of UDL. The easiest way to think of this is that we're chunking those sections of UDL down. So we've already evaluated the section of UDL on the left. Now we're going to evaluate the section of UDL in the middle here. So we have 2 meters worth to evaluate. Well, when we're stood at the 850 Newton force, we can't see any of that UDL. And it isn't until we get to the 420 Newton force that we can see all 2 meters worth of that UDL. Well, the way that we show that on our shear force diagram is at the point of the 850 Newton force, we don't see any of the UDL or that section of the UDL. And it isn't until we get to the other end that we see all 300 Newtons worth or all 2 meters worth. So we have another triangle here. This line that I've just drawn and the other sloped line for the other section of UDL should be parallel because the value of the UDLs is the same. So I've come down a further 300. Well, minus 181, which I still have in my calculator, minus 300 is minus 481. So next I have another point load to evaluate, 420 newtons. As I step away from that force to the right hand side of it, it's going to push the left side down relative to the right. So I need to come down another 420. Well, minus 481 minus 420 is minus 901. Now I still have another 1 meter section of UDL to evaluate. We haven't yet included the effects of this 1 meter section here. Well, 1 meter of UDL is only 150 newtons. So I'm going to continue down at the same angle. But this time the distance I'm travelling down is minus 150. And that takes me to minus 1051. Now we can see here that when we get to RB, or when we pass RB, so now we're stood over here somewhere, RB would be pushing the left side up relative to the right if that beam was to continue like so. So it's causing positive shear. The other reason we know it's causing positive shear is because we're at minus 1051. The magnitude of RB is 1051. And as we mentioned in the previous tutorial, that force will always return us to the 0 line. So we began at 0 on the left hand side, a shear force of 0, and we returned to a shear force of 0 on the right hand side. The reason for that was because the sum of the forces pushing downwards equals the sum of the forces pushing up. My final operation there then was plus 1051, taking me back to 0. Now that we've completed that for our shear force diagram, we're going to repeat the process, but this time we're going to repeat it in order to evaluate the bending moments. And recall that a bending moment is a force times a distance. Now let's begin at the left-hand support. At the left-hand support, the bending moment, a distance of 0 from the left-hand support, so m subscript 0, is just going to be 0. Although we're at the point of application of the force Ra, we're standing a distance of 0 from that, and anything times 0 is 0. So basically, Ra times 0 gives us the 0 there. Let's move along 1 meter. Now, when I'm at 1 meter, I can see Ra. Ra's causing positive bending because it's making the beam take on this shape. And if we refer to our convention, we can see that anything that causes the beam to take on that shape is causing positive bending. So we can say Ra times 1 Note that RA is 969 newtons. But here's the important bit. We can also see 1 meter's worth of UDL. So let's do an exploded view of what we're seeing there. When we're stood at 1 meter, we can see RA. We can also see 1 meter's worth of UDL. Well, 1 meter's worth of UDL is going to have an equivalent weight, and we've already said that each meter weighs 150 newtons. So it's going to have an equivalent weight of 150 newtons. So we have a force of 150 newtons, bearing in mind we're stood here. That force is causing negative bending because it's making the beam want to take on this shape. And that force is a distance of half a metre from where we're stood because it needs to be in the centre of that section. So that arrow that I've just drawn there represents a distance of a half a metre. We'll look at this again as we go through each of the steps. But what we need to include in our formula then is minus 150 newtons is the size of the force, and its distance from where we're stood is half a metre. Now running that through the calculator, we're going to get a bending moment at position 1 equal to RA, which is 969, minus 150 times a half, or minus 75, which is 894 Newton meters. Now let's imagine ourselves moving to 2 meters. So at 2 meters, we can see two things. We can see RA at a distance of 2 meters, causing positive bending, but we can also see 2 meters of UDL. And again, let's do a small sketch just to explain this. We have 2 meters worth of beam this time. We have RA causing positive bending because we're stood here, we're looking left, and RA is trying to bend the beam upwards, positive bending. But we then have 2 meters of UDL. 2 meters of UDL has an equivalent weight of 300 newtons, but we would need to place that in the centre of that 2 meter section. So the distance this time here is 1 meter. And it's important to note that that is causing negative bending. So we have RA at a distance of 2 meters causing positive bending, and we have 300 newtons at a distance of 1 meter causing negative bending. So let's remove that sketch and evaluate that calculation. So RA at 2 meters causing positive bending, 2 meters of UDL, so 300 newtons, at a distance of 1 meter causing negative bending, giving us 1638 Newton meters. Okay, let's go to 3 meters. Now at 3 meters, we're going to have RA causing positive bending. We're going to have 850 newtons causing negative bending. On the diagram we'll be stood here. So the 850 newtons is causing negative bending. And this time we're going to have 3 meters worth of UDL. I'll sketch this out one more time. So this time we have 3 meters worth of beam. RA, we stood over here. 850 newtons. 3 meters worth of UDL. Well, 3 times 150 is 450. And that's going to sit in the centre of this section here. Well, if this section is 3 meters long and we've just added our point load at the centre, then this distance must be 1.5 meters. RA is causing positive bending. 850 Newton force is causing negative bending. 450 newtons worth of UDL is also causing negative bending. So we have RA times 3 minus 850. We'll do the point load next. The distance there is 1 meter. And then we have 450 newtons worth of UDL at a distance of 1.5 meters. Recall that RA is 969 newtons. So running that through the calculator gives 1382 Newton meters. We'll do our next 2 points, M4. So now we're at 4 meters, so we're stood at the 420 Newton force. We're 4 meters away from RA, which is causing positive bending. We're 2 meters away from the 850 Newton force, which is causing negative bending. And we have 4 meters worth of UDL this time, so 600 newtons. And the center of the 4 meter section is at 2 meters. The distance to the equivalent point load is always half the length of the UDL. Running that through the calculator this time gives 976. Now we would expect the bending moment at the right hand support to be 0, because although we've started this process standing on the left hand support, walking from left to right and looking left, we could do that the opposite way round. We could start at the right hand support, we could move from right to left, providing we had been looking right as we did so. Now if we'd started in that way, then when we were stood at the right hand support, there wouldn't have been any forces causing a bending moment. However, I'm going to evaluate this by looking left from the right hand support, just to check that all of my calculations here work out. So from the right hand support, looking left, we have RA at a distance of 5 meters, causing positive bending. We have the 850 Newton force at a distance of 3 meters this time, causing negative bending. Now take care here, we need to make sure we include the 420 Newton force, which will also be causing negative bending if we're stood at the right hand support, so minus 420. And its distance from our position is 1 meter. And finally, we have 5 meters worth of UDL. And we can add this to our main diagram. We've got 5 times 150 is 750. And it would be added to the center of that 5 meter section. So 750 newtons. This distance here is going to be 2.5 meters. So minus 750 times 2.5. So evaluating that, we get an answer of 0. And that's exactly as we would expect. The very last step then is to sketch our bending moment diagram. And if we look at each of those bending moments, we can see that the maximum bending moment, we go from 894 to 1638 and then back down to 1382, 976. So the maximum bending moment is 1638 Newton meters, occurring 2 meters from the left hand support. So let's add that there. And the magnitude was plus 1638 Newton meters. The other thing we know is that the bending moment at the left hand support is 0. The bending moment at the right hand support is 0. So we can sketch our bending moment diagram. The alternative to this would have been to add the values at 1 meter, 3 meters, 4 meters, and so on. But as mentioned in the previous video, as engineers, what we're really interested in is the maximum bending moment acting on that beam, because that's the point where the beam's most likely to fail.